Pyrolysis. The pyrolysis or devolatilization process is the thermal decomposition of materials at elevated temperatures in an inert atmosphere. It involves a change of chemical composition. The word is coined from the Greek-derived elements pyro, fire, and lysis, separating. Pyrolysis is most commonly used in the treatment of organic materials. It is one of the processes involved in charring wood. In general, pyrolysis of organic substances produces volatile products and leaves char, a carbon-rich solid residue. Extreme pyrolysis, which leaves mostly carbon as the residue, is called carbonization. Pyrolysis is considered the first step in the processes of gasification or combustion. The process is used heavily in the chemical industry, for example, to produce ethylene, many forms of carbon, and other chemicals from petroleum, coal, and even wood, to produce coke from coal. It is used also in the conversion of natural gas, primarily methane, into non-polluting hydrogen gas and non-polluting solid carbon char recently on an industrial scale. Aspirational applications of pyrolysis would convert biomass into syngas and biochar, waste plastics, back into usable oil, or waste into safely disposable substances. Terminology. Pyrolysis is one of the various types of chemical degradation processes that occur at higher temperatures above the boiling point of water or other solvents. It differs from other processes, like combustion and hydrolysis, in that it usually does not involve the addition of other reagents, such as oxygen (O2) in combustion or water in hydrolysis. Pyrolysis produces solids char, condensable liquids tar, and uncondensing/permanent gases. Types of pyrolyses. Complete pyrolysis of organic matter usually leaves a solid residue that consists mostly of elemental carbon. The process is then called carbonization. More specific cases of pyrolyses include methane pyrolyses, in the presence of catalytic molten metals for the direct conversion of methane to non-polluting hydrogen fuel and separable solid carbon. Hydrous pyrolyses, in the presence of superheated water or steam, producing hydrogen and also substantial atmospheric carbon dioxide, also used in oil refining. Dry distillation, as in the original production of sulfuric acid from sulfates. Destructive distillation, as in the manufacture of charcoal, coke, and activated carbon. Caramelization of sugars. High-temperature cooking processes, such as roasting, frying, toasting, and grilling. Charcoal burning, the production of charcoal. Tar production by pyrolysis of wood in tar kilns. Cracking of heavier hydrocarbons into lighter ones, as in oil refining. Thermal depolymerization, that breaks down plastics and other polymers into monomers and oligomers. Ceramization, involving the formation of polymer-derived ceramics from preceramic polymers under an inert atmosphere. Catagenesis, the natural conversion of buried organic matter to fossil fuels. And flash vacuum pyrolyses, used in organic synthesis. General processes and mechanisms. Pyrolysis generally consists in heating the material above its decomposition temperature, breaking chemical bonds in its molecules. The fragments usually become smaller molecules, but may combine to produce residues with larger molecular mass, even amorphous covalent solids. In many settings, some amounts of oxygen, water, or other substances may be present, so that combustion, hydrolysis, or other chemical processes may occur besides pyrolysis proper. Sometimes those chemicals are added intentionally, as in the burning of firewood, in the traditional manufacture of charcoal, and in the steam cracking of crude oil. Conversely, the starting material may be heated in a vacuum or in an inert atmosphere to avoid chemical side reactions such as combustion or hydrolysis. Pyrolysis in a vacuum also lowers the boiling point of the byproducts, improving their recovery. When organic matter is heated at increasing temperatures in open containers, the following processes generally occur in successive or overlapping stages. Below about 100 deg C volatiles, including some water, evaporate. Heat-sensitive substances, such as vitamin C and proteins, may partially change or decompose already at this stage. At about 100 deg C or slightly higher, any remaining water, this process consumes a lot of energy, so the temperature may stop rising until all water has evaporated. Water trapped in crystal structure of hydrates may come off at somewhat higher temperatures. Some solid substances, like fats, waxes, and sugars, may melt and separate. Between 100 and 500 deg C, many common organic molecules break down. Most sugars start decomposing at 160–180 deg C. Cellulose, a major component of wood paper, and cotton fabrics, decomposes at about 350 deg C. Lignin, another major wood component, starts decomposing at about 350 deg C, but continues releasing volatile products up to 500 deg C. The decomposition products usually include water, carbon monoxide CO and or carbon dioxide CO2, as well as a large number of organic compounds. Gases and volatile products leave the sample, and some of them may condense again as smoke. Generally, this process also absorbs energy. Some volatiles may ignite and burn, creating a visible flame. The non-volatile residues typically become richer in carbon and form large disordered molecules with colors ranging between brown and black. At this point, the matter is said to have been charred or carbonized. At 200–300 deg C, if oxygen has not been excluded, the carbonaceous residue may start to burn in a highly exothermic reaction, often with no or little visible flame. Once carbon combustion starts, the temperature rises spontaneously, turning the residue into a glowing ember and releasing carbon dioxide and or monoxide. At this stage, some of the nitrogen still remaining in the residue may be oxidized into nitrogen oxides like N-O and N2O3. Sulfur and other elements like chlorine and arsenic may be oxidized and volatilized at this stage. Once combustion of the carbonaceous residue is complete, a powdery or solid mineral residue, ash is often left behind, consisting of inorganic oxidized materials of high melting point. Some of the ash may have left during combustion, entrained by the gases as fly ash or particulate emissions. Metals present in the original matter usually remain in the ash as oxides or carbonates, such as potash. Phosphorus, from materials such as bone, phospholipids, and nucleic acids, usually remains as phosphates. Occurrence and uses. Cooking. Pyrolysis has many applications in food preparation. Caramelization is the pyrolysis of sugars in food, often after the sugars have been produced by the breakdown of polysaccharides. The food goes brown and changes flavor. The distinctive flavors are used in many dishes. For instance, caramelized onion is used in French onion soup. The temperatures needed for caramelization lie above the boiling point of water. Frying oil can easily rise above the boiling point. Putting a lid on the frying pan keeps the water in, and some of it recondenses, keeping the temperature too cool to brown for longer time. Pyrolysis of food can also be undesirable, as in the charring of burnt food at temperatures too low for the oxidative combustion of carbon to produce flames and burn the food to ash. Coke, carbon, charcoals, and chars. Carbon and carbon-rich materials have desirable properties but are non-volatile, even at high temperatures. Consequently, pyrolysis is used to produce many kinds of carbon. These can be used for fuel, as reagents in steelmaking coke, and as structural materials. Charcoal is a less smoky fuel than pyrolyzed wood. Some cities ban or used to ban wood fires when residents only use charcoal, and similarly treated rock coal, called coke. Air pollution is significantly reduced. In cities where people do not generally cook or heat with fires, this is not needed. In the mid-20th century, smokeless legislation in Europe required cleaner burning techniques, such as coke fuel and smoke-burning incinerators, as an effective measure to reduce air pollution. The coke making or coking process consists of heating the material in coking ovens to very high temperatures, up to 900 deg C or 1700 deg F, so that the molecules are broken down into lighter volatile. The amount of volatiles varies with the source material, but is typically 25–30% of it by weight. High-temperature pyrolysis is used on an industrial scale to convert coal into coke. This is useful in metallurgy, where the higher temperatures are necessary for many processes, such as steelmaking. Volatile byproducts of this process are also often useful, including benzene and pyridine. Coke can also be produced from the solid residue left from petroleum refining. The original vascular structure of the wood and the pores created by escaping gases combine to produce a light and porous material. By starting with a dense wood-like material, such as nutshells or peach stones, one obtains a form of charcoal with particularly fine pores and hence a much larger pore surface area, called activated carbon, which is used as an adsorbent for a wide range of chemical substances. Biochar is the residue of incomplete organic pyrolyses, e.g. from cooking fires. It is a key component of the terra preta soils associated with ancient indigenous communities of the Amazon basin. Terra preta is much sought by local farmers for its superior fertility and capacity to promote and retain an enhanced suite of beneficial microbiota compared to the typical red soil of the region. Efforts are underway to recreate these soils through biochar, the solid residue of pyrolyses of various materials, mostly organic waste. Carbon fibers are filaments of carbon that can be used to make very strong yarns and textiles. Carbon fiber items are often produced by spinning and weaving the desired item from fibers of a suitable polymer, and then pyrolyzing the material at a high temperature from 1500–3000 deg C or 27–35,430 deg F. The first carbon fibers were made from rayon, but polyacrylonitrile has become the most common starting material. For their first workable electric lamps, Joseph Wilson Swan and Thomas Edison used carbon filaments made by pyrolyses of cotton yarns and bamboo splinters, respectively. Pyrolysis is the reaction used to coat a preformed substrate with a layer of pyrolytic carbon. This is typically done in a fluidized bed reactor heated to 1000–2000 deg C or 18–33,630 deg F. Pyrolytic carbon coatings are used in many applications, including artificial heart valves. Liquid and gaseous biofuels. Pyrolysis is the basis of several methods for producing fuel from biomass, i.e. lignocellulosic biomass. Crops studied as biomass feedstock for pyrolysis include native North American prairie grasses such as switchgrass and bred versions of other grasses such as Miscanthus giganteus. Other sources of organic matter as feedstock for pyrolysis include green waste, sawdust, waste wood leaves, vegetables, nutshells, straw, cotton trash, rice hulls, and orange peels. Animal waste including poultry litter, dairy manure, and potentially other manures are also under evaluation. Some industrial byproducts are also suitable feedstock, including paper sludge, distillers' grain, and sewage sludge. In the biomass components, the pyrolysis of hemicellulose happens between 210 and 310 deg C. The pyrolysis of cellulose starts from 300–315 deg C and ends at 360–380 deg C, with a peak at 342–354 deg C. Lignin starts to decompose at about 200 deg C and continues until 1000 deg C. Synthetic diesel fuel by pyrolysis of organic materials is not yet economically competitive. Higher efficiency is sometimes achieved by flash pyrolyses, in which finely divided feedstock is quickly heated to between 350 and 500 deg C, 660 and 930 deg F for less than 2 seconds. Syngas is usually produced by pyrolyses. The low quality of oils produced through pyrolyses can be improved by physical and chemical processes, which might drive up production costs, but may make sense economically as circumstances change. There is also the possibility of integrating with other processes, such as mechanical biological treatment and anaerobic digestion. Fast pyrolysis is also investigated for biomass conversion. Fuel bio-oil can also be produced by hydrous pyrolyses. Methane pyrolysis for hydrogen. Methane pyrolysis is a non-polluting industrial process for turquoise hydrogen production from methane by removing solid carbon from natural gas. This one-step process produces non-polluting hydrogen in high volume at low cost, less than steam reforming, with carbon sequestration. Only water is released when hydrogen is used as the fuel for fuel cell electric heavy truck transportation, gas turbine electric power generation, and hydrogen for industrial processes, including producing ammonia fertilizer and cement. Methane pyrolysis is the process operating around 1065 deg-C for producing hydrogen from natural gas that allows removal of carbon easily. Solid non-polluting carbon is a byproduct of the process. The industrial quality solid carbon can then be sold or landfilled and is not released into the atmosphere, avoiding emission of greenhouse gas GHG or groundwater pollution from a landfill. Volume production is being evaluated in the Bass Methane Pyrolysis at Scale pilot plant, the chemical engineering team at University of California, Santa Barbara, and in such research laboratories as Karlsruhe Liquid Metal Laboratory Cala. Power for process heat consumed is only 1/7 of the power consumed in the water electrolysis method for producing hydrogen. Ethylene. Pyrolysis is used to produce ethylene, the chemical compound produced on the largest scale industrially 110 million tons/year in 2005. In this process, hydrocarbons from petroleum are heated to around 600 deg-C 1112 deg-F in the presence of steam. This is called steam cracking. The resulting ethylene is used to make antifreeze ethylene glycol, PVC via vinyl chloride, and many other polymers, such as polyethylene and polystyrene. Semiconductors. The process of metal organic vapor phase epitaxy MOCT entails pyrolysis of volatile organometallic compounds to give semiconductors, hard coatings, and other applicable materials. The reactions entail thermal degradation of precursors, with deposition of the inorganic component and release of the hydrocarbons as gaseous waste. Since it is an atom-by-atom deposition, these atoms organize themselves into crystals to form the bulk semiconductor. Silicon chips are produced by the pyrolysis of silane, CH4C plus 2H2. Gallium arsenide, another semiconductor, forms upon co-pyrolyses of trimethyl gallium and arsine. Waste management. Pyrolysis can also be used to treat municipal solid waste and plastic waste. The main advantage is the reduction in volume of the waste. In principle, pyrolysis will regenerate the monomers precursors to the polymers that are treated, but in practice the process is neither a clean nor an economically competitive source of monomers. In tire waste management, tire pyrolysis is a well-developed technology. Other products from car tire pyrolysis include steel wires, carbon black, and bitumen. The area faces legislative, economic, and marketing obstacles. Oil derived from tire rubber pyrolysis has a high sulfur content, which gives it high potential as a pollutant and should be desulfurized. Alkaline pyrolysis of sewage sludge at low temperature of 500 deg-C can enhance H2 production with in situ carbon capture. The use of NaOH has the potential to produce H2-rich gas that can be used for fuels cells directly. In early November 2021, the U.S. state of Georgia announced a joint effort with Igneo Technologies to build an $85 million large electronics recycling plant in the port of Savannah. The project will focus on lower-value, plastics-heavy devices in the waste stream using multiple shredders and furnaces using pyrolysis technology. Thermal cleaning. Pyrolysis is also used for thermal cleaning, an industrial application to remove organic substances such as polymers, plastics, and coatings from parts, products, or production components like extruder screws, spinnerets, and static mixers. During the thermal cleaning process, at temperatures between 310 C to 540 C 600 deg F to 1000 deg F, organic material is converted by pyrolysis and oxidation into volatile organic compounds, hydrocarbons, and carbonized gas. Inorganic elements remain. Several types of thermal cleaning systems use pyrolyses. Molten salt baths belong to the oldest thermal cleaning systems. Cleaning with a molten salt bath is very fast but implies the risk of dangerous splatters or other potential hazards connected with the use of salt baths, like explosions or highly toxic hydrogen cyanide gas. Fluidized bed systems use sand or aluminium oxide as heating medium. These systems also clean very fast, but the medium does not melt or boil, nor emit any vapors or odors. The cleaning process takes 1 to 2 hours. Vacuum ovens use pyrolyses in a vacuum, avoiding uncontrolled combustion inside the cleaning chamber. The cleaning process takes 8 to 30 hours. Burn-off ovens, also known as heat cleaning ovens, are gas-fired and used in the painting, coatings, electric motors, and plastics industries for removing organics from heavy and large metal parts. Fine chemical synthesis. Pyrolysis is used in the production of chemical compounds, mainly, but not only, in the research laboratory. The area of boron hydride clusters started with the study of the pyrolyses of diborane B2H6 at Ca. 200 deg C. Products include the clusters pentaborane and decaborane. These pyrolyses involve not only cracking to give H2, but also recondensation. The synthesis of nanoparticles, zirconia, and oxides utilizing an ultrasonic nozzle in a process called ultrasonic spray pyrolysis USB. Other uses and occurrences. Pyrolysis is used to turn organic materials into carbon for the purpose of carbon-14 dating. Pyrolysis of tobacco, paper, and additives in cigarettes and other products generates many volatile products, including nicotine, carbon monoxide, and tar, that are responsible for the aroma and negative health effects of smoking. Similar considerations apply to the smoking of marijuana and the burning of incense products and mosquito coils. Pyrolysis occurs during the incineration of trash, potentially generating volatiles that are toxic or contribute to air pollution if not completely burned. Laboratory or industrial equipment sometimes gets fouled by carbonaceous residues that result from coking, the pyrolyses of organic products that come into contact with hot surfaces. pH generation. Polycyclic aromatic hydrocarbons pH can be generated from the pyrolyses of different solid waste fractions, such as hemicellulose, cellulose, lignin, pectin, starch, polyethylene P, polystyrene PS, polyvinyl chloride PVC, and polyethylene terephthalate PT. PS, PVC, and lignin generate significant amount of pH. Naphthalene is the most abundant pH among all the polycyclic aromatic hydrocarbons. When the temperature is increased from 500 to 900 deg C, most pH increase. With increasing temperature, the percentage of light pH decreases and the percentage of heavy pH increases. Study tools, D-tools. Thermogravimetric analysis. Thermogravimetric analysis (TGA) is one of the most common techniques to investigate pyrolyses with no limitations of heat and mass transfer. The results can be used to determine mass loss kinetics. Activation energies can be calculated using the Kissinger method or peak analysis least square method PALSM. TGA can couple with Fourier transform, infrared spectroscopy (FTIR), and mass spectrometry. As the temperature increases, the volatiles generated from pyrolyses can be measured. Macro TGA. In TGA, the sample is loaded first before the increase of temperature, and the heating rate is low, less than 100 deg C-1. Macro TGA can use gram-scale samples, which can be used to investigate the pyrolyses with mass and heat transfer effects. Pyrolysis gas chromatography mass spectrometry. Pyrolysis mass spectrometry (PGCMS) is an important laboratory procedure to determine the structure of compounds. History. Pyrolysis has been used for turning wood into charcoal since ancient times. In their embalming process, the ancient Egyptians used methanol, which they obtained from the pyrolysis of wood. The dry distillation of wood remained the major source of methanol into the early 20th century. Pyrolysis was instrumental in the discovery of many important chemical substances, such as phosphorus from ammonium sodium hydrogen phosphate and H4NO offer in concentrated urine, and oxygen from mercuric oxide and various nitrates.